The search for the true nature of light goes back centuries and includes contributions from some of the most illustrious scientists in history. To the ancient Egyptians, light was the gaze of their supreme god Ra, and emanated from the sun and the moon's Ra's eyes. The ancient Greek believed the reverse Pythagoras thought internal fires in the human eyes humiliated the world, while Plato believed sight was only possible when the fires of eye meet and combine with daylight, the fire of the sun.
Good morning, class. Today we are going to embark on an intriguing journey into the mysterious world of light. We all know that light allows us to see and perceive the world around us. But have you ever wondered about its true nature? Is light just a wave or it's composed of tiny particles? Well, prepare to be amazed because today we will explore the dual nature of light and revealing its fascinating characteristic as both a wave and a particle.
Particle theory or corpuscular theory. The particle theory of light was indeed proposed by Sir Isaac Newton in the 17th century. Newton suggested that light consists of tiny particles called corpuscles. According to his theory, these corpuscles travel in straight lines and interact with matter-like particles, explaining various optical phenomena. The wave theory of light was primarily developed by Christian Huygens, a Dutch physicist and mathematician in the 17th century. Huygens proposed that light propagates as a wave, with each point of the wavefront acting as a source of secondary spherical wavelets. The wave theory explained phenomena like diffraction and interference and was an alternative explanation to Newton's particle theory.
Light is a form of electromagnetic radiation. It is the natural agent that stimulates sight and makes things easy to see. Light is a form of electromagnetic radiation that shows properties of both waves and particles. It is a form of energy. Light also keeps the earth warm. Reflection and refraction are fundamental phenomena related to the behavior of light when it interacts with boundaries between different media. Reflection occurs when light encounters a surface and bounces back into the same medium from which it originated. Examples of reflection include light bouncing off a mirror or the surface of a still body of water. Refraction occurs when light passes from one medium to another and it changes direction due to the change in its speed both. Reflection and refraction are essential phenomena.
Our topic is photon concept. Photon, waves of electromagnetic radiation. It has no charge, it has no resting mass, it travels at the speed of light. A photon is an elementary particle that is a quantum of the electromagnetic field, including electromagnetic radiation such as light and radio waves, and the force carrier for the electromagnetic force. Photon energy. Photon energy is directly proportional to the frequency. It is inversely proportional to its wavelength. This is due to the amount of energy is proportional to the electromagnetic frequency of photon. If the frequency of the photon is high, its energy is also high. If the wavelength of the photon is longer, then the energy is lower.
Reason why red light is used in photographic darkrooms. First, light-sensitive photographic paper would not be overexposed and ruin the process. Second, red light has a wavelength of 650 nm and a frequency of 4.62 Hz. So, it implies that red light carries low energy not sufficient enough to be able to process the photographic film. Reason why ultraviolet light gives sunburn. UV light damages skin cells and the immune system reacts by increasing blood flow to the affected areas, which causes inflamed skin or what we call sunburn. UV light spans a range of wavelengths between 10 and 400 nm and a frequency of between 800 THz and 30,000 THz. So, you can get sunburn on cool or even cloudy days. Even surfaces like snow, sand, and water can even reflect UV rays and burn skin.
And here we see a table of different photon lights. Here it shows the color, wavelength, frequency, and photon energy. The different colors are violet, blue, green, yellow, orange, and red. The color we associate with a photon depends on its energy, which is proportional to its frequency.
Wave behavior of electrons. John Joseph Thomson and his son George Thomson shared one common thing, their scientific discoveries with electrons. Joseph John Thomson won a Nobel Prize with his discovery of the electron, the first subatomic particle to be discovered.
Wave properties of light. Dispersion. Dispersion is the separation of white light into a spectrum of colors by the process of refraction. Scattering. Scattering is the process where light rays deviate from its path due to non-uniformities in the medium through which they pass. Interference. Interference is a phenomenon that occurs when two light waves meet while traveling along with the same medium. Superposition principle is the basic principle used in the interference of light. Incoming light waves can either superimpose constructively or destructively. If they combine constructively, the intensity increases, while when they add destructively, it decreases. Types of interference. A. Constructive interference occurs at any location along with the medium where the two interfering waves have a displacement in the same direction. For example, the crest of a one wave meets the crest of a second wave. They will interfere in such a manner as to produce a supercrest. Similarly, interference of a trough and a trough produces a supertrough. In this case, the intensity of the wave increases.
Active interference occurs when two interfering waves are with opposite displacement. For example, a crest meets with a trough. Destructive interference often decreases the resulting displacement of a wave. Diffraction is a process in which a light ray travels through an obstacle or around the barrier and it spread out as a result. For example, sending light rays through a slit well spread out that makes a wider stream of light. In this experiment, we witness a different colors of lights, of which the cellophane act as a filter with the designated colors. First, we emit the actual light of a flashlight and we observe that the three boxes reflect its original colors. Now with the individual colors, which are blue, green, and red. If we use the red cellophane, we observe a red light emitted to the boxes and we can see the change of the color boxes corresponding to the light it's received. On to the next color, if we use the blue cellophane, we also observe a blue light emitted to the boxes and we can see the change of the color corresponding to the light it's received. And lastly, the green. If we use the green cellophane, we also observe a green light emitted to the boxes and we can see the change of the boxes corresponding to the light it received.